at some point in the middle of the class will say, okay, I want you to do this. So either you on your own or with the person sitting next to you, depending if it's in a small class, maybe around the table, work on this problem. And then I'll ask for solutions. I won't be so cruel as to make you go to the board and present a solution, which does happen quite frequently actually in other classes. But I will ask you to explain to me how to do something. It's a way better way to stay awake than to listen to a professor talk for 75 minutes. So anyway, that was a way of saying I won't be talking for 5 minutes. All right. So now I ask you a question. In your experience, how is math used in science? Tom, who is up there? Just name some ways it's used. Yep.
Rate of population growth.
Let's start with size. So it's a measuring tool. See, you went to the second use right away. We measure with numbers, real numbers, counting numbers. Almost anything we do involves some kind of enumeration or weighing or something, an assignment of numerical values too. And so population size would be an example. But as well as using numbers to name things like the weight or the height or the number, mathematics is also used to describe how something like a population might change, or perhaps how the length of the day might change over the course of a year. And this involves the creation of sort of mathematical descriptions for whatever it is we're interested in measuring or describing. Now, those descriptions can be very, very complicated and sophisticated. So you turn on channel, how many of you are from Atlanta? Okay, so every morning, Severe Weather Center 2, Karen Minton explains that she's going to show us a new model of what's going to happen during the day. Well, it's sort of the same as a mathematical model. It's a computer model. And what she means by a new model is you take a bunch of new data and plug it into a computer program, and that computer program is so sophisticated and beautiful that it creates the images of the thunderstorms that are going to take place over the course of the day, which has been happening a lot here lately. So meteorological models are very sophisticated models that make use of a lot of computing, but underneath there's a lot of mathematics that goes into describing how the weather is going to be changing. Simpler than that would be something like a population model. So let's take something like population at time t is given by P of t. Now, if we're thinking of a population of humans, then this could be a counting number, and t could be years from some base year. Or if it was a bacterial colony or growth in a chemostat or a lab device of some kind, then P of t might be micrograms, and t might be minutes. Units in both for what you're measuring and time dependent on, of course, what you're dealing with. Now, there's one kind of population model that's very well known, and it starts from an assumption that's appropriate for something, say, like a single-cell organism that's growing by cell division. So, for instance, you might have something that a room, a tree. What this is supposed to indicate is that after 1, 2, 3 minutes, no, maybe this is just 1 minute. Or maybe it's 1 hour. We have 3 divisions, 3 sets of divisions. So for every original bacterium, we now have how many? Now, what this will mean is that if the population at time 0 is, I don't know, maybe an easy number, 10, then the population at time 1 is going to be 10 times 8, yeah, 8. Okay, 2, 10 times 8 times, remember, in another minute, how many times is this going to?
8 more.
8 more.
So it's 60.
And now the magic of exponentiation. After t hours, pardon me, I've got this many. If I started with 10, I'll have this many. Well, that's what's called an exponential function, and this is what's called exponential growth. So where did exponential growth come from? It came from the assumption that the rate of growth in the population is proportional to the size of the population. So because the division takes place at every step, then if you just take the total number you start with and multiply by the appropriate factor, you'll get the result after so many minutes or so many hours. The magic phrase is the rate of growth of the population is proportional to the size of the population. So if you have something like bacterial growth, which obeys this, then the consequence is exponential growth. No choice. Other things obey this. What happens to a bank account would obey this. Now, the multiplying factor is not nearly as large as you will be able to. Anybody who's put money in a savings account knows that it's going to be something more like P of t is the initial principal times 1.0001 to the t. You don't get much anymore. But anyway, it's still exponential growth. There's also exponential decay. Or decrease. We often hear the phrase exponential decay because the model is being applied to the behavior of a radioactive isotope. So you've got something like carbon-14 or any other, I never remember the numbers of neutrons, so let's stick with carbon-14. And the rate of decay is proportional to the amount of carbon-14 present, which means that the equation is going to be something like C of t is the initial amount times, and now here, it's typical to use the Euler E, 2.7 something, e to the minus kt. Here I could have written this as 10 times e to the, well, it'd be silly. The natural logarithm of 8, that's just 8 again. But it makes more sense to use the integer. The typical way that an exponential growth or decay function is written is like this. And there's the variable up there making the integer exponential.